Code monkey, get up, get coffee. Code monkey, go to job. Code monkey, have boring meeting with boring manager Rob. Rob say code monkey very diligent, but his output stink. His code not functional or elegant. What do code monkey think? Code monkey think maybe manager wanna write goddamn login page himself. Code monkey not say it out loud. Code monkey not crazy, just proud. Code monkey like Fritos. Code monkey like Tab and Mountain Dew. Code monkey very simple man with big warm fuzzy secret heart. Code monkey like you.
It's very funny because, of course, it's appropriate to put on our throat.
Code monkey like
people making fun of this concept of essentially
Code monkey hang around at front desk till your sweater look nice. Code monkey offer buy you soda, bring you cup, bring you ice. You say no thank you for the soda, cause soda make you fat. Anyway, you busy with the telephone, no time for chat. Code monkey have long walk back to cubicle. He sit down, pretend to work. Code monkey not thinking so straight. Code monkey not feeling so great. Code monkey like Fritos. Code monkey like Tab and Mountain Dew. Code monkey very simple man with big warm fuzzy secret heart. Code monkey like you.
Code monkey is what we sort of call the idea of someone who just writes programs but using their fingers all day, every day, not using this or this all day, every day. And of course, we want a job that uses these things. Okay, so Code Monkey, but the song wasn't finishing. It was building up to finishing, and it was nearly finishing, and then I listened and listened, and it still had like 20 seconds to go. And that reminded me of Harry Potter, because that's been building up to finishing. You know, it's just this like climax. It's building up and building up. It's like a Terry Pratchett book. You know, he starts the climax halfway through the book now, getting to the end. Okay, so I did stop it, but thank you for whoever put that up, because I really like this notion of us celebrating geekiness and finding songs that lift our hearts about other people rejoicing, being, you know, just being themselves. So that's really good. So skepticism and rejoicing in individuality I really like. Let's jump on now. I want to teach you something that you may or may not have already seen, depending on if I've taught you before. I have noticed, I've noticed that, I noticed a lot of people failed the prac exam. B, I noticed that not everyone is getting 2 marks for each lab. And C, the tutors are telling me that some students are nervous about their programming ability. And all of these things are freaking me out completely. So, because past experience has shown that if you do all your labs and get full marks for lab marks, it's not much of a predictor for anything in terms of your final mark, because most people manage to pull it off. But if you don't get all your lab marks, it's a very strong predictor for failing the course. So I don't want people to be thinking, oh, I'm getting 1 out of 2 for my lab. Woohoo, 50%, that's a pass. No, it's not. It's not. It means, no. So if you're getting less than 75% for your lab marks, it's this warning. That's about the cutoff for the lowest passing thing. So we just expect you to be able to program. Now maybe you're having problems with programming. So I was trying to think of all the ways I could help people. So I'm sort of open to suggestions. We've got some very smart people in this room. In fact, you're all very smart. And you've all navigated some computing courses, so you're all quite capable of putting the effort in and sticking and persevering and not giving up. And you've all faced personal challenges the first time you've had to program and it didn't make any sense, and you've moved on till you can do things. So you've all succeeded and moved through that process. So you have what it takes. You have the right stuff, as NASA would call it. But somehow now your code confidence seems to have dropped. Maybe because we've gone too long without programming? I don't know what it is. So how can we help you if you're a nervous programmer? How can we help you with your programming? What could we do? I'm open to suggestions for the next 2 or 3 minutes. Just shoot your hand up if you're nervous about programming, if you can think of a single thing I can do to help. One thing is, thanks, okay.
Turn all your lectures into geeky songs.
Turn all lectures into geeky songs. No, no. So we have geeky songs because that's interesting and motivational and things like that, but we can't just have that. You know, it has to motivate you to then do something. It can't just motivate you to listen to more geeky songs. It has to motivate you to go home and think, I want to be like that guy. I can do that if only I do my lab exercises. That's, you know, I like that. So yeah. More code? Code problems or just samples of C code? Okay. Maybe we should start posting lab solutions. What do you think? Okay. Now, of course, that raises problems for the person that teaches the course next time because they'll have to think of their own questions. But actually, I think that's fair enough. Okay. Should I post student solutions with commentary? Should I just post not perfect solutions, but like model solutions, sample solutions? Commentary. Okay. Can someone remember this? Who's doing the Ricky notes this week? Who's in the third tute? You're doing the whole notes? Have you been running like a maniac? You haven't written anything?
I've written some.
Okay. Oh, okay. So what tute are you in? Who's your tutor? Tim Wiley, Wednesday at 12? Wednesday at 4. Who else is in Tim Wiley's Wednesday at 4 tute? Are you guys running notes like lunatics? Oh, fantastic. Okay. Phew. It's all under control. Can you guys keep track of this list of suggestions? Just put it on the wiki. So one is code samples, both commentary and sample solutions for labs. Other ideas? Shh, 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 shh. But you know, seeing code does not help you program. That's like getting someone to lift the weights for you. The only way you can learn to practice, the only way you can learn to program is if you do it. You have to do it. Talking about it, reading it, listening to it, writing songs about it, laughing about it, watching someone else program. None of these things move you one step closer to being able to program. There's only one way of learning how to program, and that is sitting down and programming and failing and trying and failing and trying and putting in, I think I said we're expecting 11 hours a week. So that's 3 hours a week sort of home practice, I reckon, in the early part of the course when everything's easy. And if you can't program, you're entering this course and your programming's weak, that 11 hours a week was assuming you could program. So just mentally up your notch and think, okay, no fun for a couple more weeks then, and just, no, except programming fun, and just do heaps of home programming. So yes, you've got to practice. What else? There was another hand. Yes?
Maybe some small problems without solutions.
Give you small problems? I have, what about releasing the prac questions, exam questions? Would that be useful? All right. I was thinking of keeping them up my belt so we could apply the same questions to next year's lot to sort of see if there's a difference from year to year. But information about the questions is going to leak anyway, isn't it? So I might as well release it. So can you remember that? Yep.
Aren't you lucky that the wiki is only weak access and it scares people?
Oh, yeah, but it leaks. Information leaks. Anyone at a college steals all the information. No, people don't do it. Can you say a really long, hard to spell word?
Newman ultra microscopic silica volcano.
Can you say a really long, hard to spell word?
Anti-disestablishmentarian.
Well done, thank you. So that's got to be in the notes now. I'm making them say words they have to write down themselves. It's just being cruel. Actually, I was at a meeting once and someone said they were really cross when some committee was disestablished. And I said, would it be fair to say that you were against that? And they said yes. And I said, I was anti that too. And they said, good. And I just felt really happy. No one else did. Okay. There are longer words, like smiles.
Apparently the
Yes.
word for fear of long words is hippopotamonstrous.
Fear of long words. Can you write that down? That's a really funny joke. That should be in the notes. Fear of long words is something involving hippopotamus. Can you tell them, or just look it up? Yeah. Awesome. Fantastic. So anyone that wants to say difficult things for them to write down, please go for it. Okay, so what I want to teach you right now. Oh no, let me get two more suggestions from you guys, and then I'm going to tell you what I've already thought of, but I'm going to do your things as well. Because I haven't been sitting idle, I've been worrying about it. What else can I do to help you? If there's anything, remember we run the repeater tube with David? Now David, I've got to be honest, is quite obnoxious. And he smells. And what else is bad about that? Oh, David, there you are. David, tell everyone how nice you are. Yeah. David is the loveliest guy in the world and the smartest guy in the world simultaneously. If you're having problems programming, or if you failed the prac exam, switch to David's tute. It runs on Friday afternoons. Take a pank, but it's worth it. No, so David will look after everyone that switches to his tute. Only 5 people have elected to switch. Now, there were more than 100 people who failed the prac exam, so the other 95 of you, I hope, have other plans. I hope you're not thinking it's okay, because we've got to fix the problem. We can't just worry about it and not do anything about it. We've got to fix it, and hopefully in the next week or two. So we've got code samples, me giving you code samples, me releasing more questions, me releasing answers. There's a lot of work for me here. I don't see your muscles getting bigger. What can we do to get you to do it? I want you to do something to improve your coding. Just do it. But do what? What's that? Make. No. Okay. All right, we've descended into anarchy, so we're going to move off this thing, and I'm going to tell you my idea. I'm going to just re-explain a few concepts that hopefully you'll already know, but you might need a refresher on. And I'm also going to point you to the videos we did when we did this course a couple of years ago, or last year, the first semester last year, so you can go and look at those and learn some stuff. And I'll release tutes and labs from that year too, maybe. Oh, I don't know if I can. But I'll release as much stuff as I can. And I'll get Maury, who took you last semester for 1917, to release all those tutes and labs if we can, so you can have another whack at trying them. Yes?
Can we get course notes for this course? Because 1917...
Can you get course notes for this course?
Yes.
Yes?
But, I mean, like 19...
Oh, me write them?
Yes.
I love all your suggestions. They're fantastic. That's excellent. I'm going to have enormous muscles at the end of this course. Now, we have course notes for the course, but who's writing them? This is wiki. Yeah. You're writing the course notes. Every day, you guys are writing the course notes on the wiki.
Oh, no, I meant the course notes at 1917 now, basically. Just got...
Oh, sorry. I was making fun of you. I feel mortified. No, I feel... what does that make me? A motivator. Anyway. Can't get it. So what, you want the 1917 course notes?
No, make 1927 course notes.
Who makes them? Me?
No, I don't know who makes them. Someone made the 1917.
Okay, you guys are making course notes. There are no course notes for this course. You guys are making some on the wiki, and at the end we're going to print them out and you get to keep them. Okay, but there are none for this course. There's a textbook you can read, but we have no summary of the course except what each tute in turn is writing each day. But it's not this course that's the problem that I'm worried about at the moment. I'm worried about the programming ability from the last course. Yeah, that's my concern. Okay, so here's my, good addition. I'm not saying there's no problem with this course. There could be, but I'm just facing one problem at a time. Yeah. So I'm going to explain some stuff, and to explain anything in C, you've got to talk about pointers, because that's where we fall down. And to talk about pointers, well, I like talking about them through machine code. So I'm going to show you a very, very simple machine code that's also in the tutes and labs this week. And it's called it's based on a very famous computer chip it's the 16 address linear executor chip, and it's the 4241 chip. It's a very famous one. The 4 at the front tells you it's a 4-bit machine. If it's a 4-bit machine, how big is each memory location? 4 bits. And what numbers can be stored in each memory location? 0 to 15. And how many memory locations can it have then? It can only have 15 at most, because you can't talk about other memory locations. Well, not easily. It can only have 15 bytes of memory. Plus on the side, it has 16. It has two special things, thank you, called registers. Register 0, register 1. And they each hold 4 bits. So this is the entire memory. We've written the entire memory out here. We're going to use this machine to demonstrate concepts about pointers as we come up to them. So don't do what some students did in a course that I taught back in 1917, back in 2008. When I talked about the machine code in one lecture, they thought, oh, that was different to anything I've ever seen before. That was confusing. I don't know if I understood that. Ah, well, I'll never need to know that again. And then to their horror, each week, I kept coming back to it and it got more and more elaborate. But they were doomed because they'd missed the first one and then it was in the exam and then, So please do pay attention to this, and if it doesn't make sense, make sure you can do it in your tute with your tutor this week. Here's how it goes. I've written the instructions up on the board here. Here we are. Here are the instructions. Shh, 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 shh. It is the world's simplest machine. No, we're not worrying about anything. This is the world's simplest machine. It's got 16 memory addresses. Can you see them? Shh, 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 shh. Can you you want some light? Who said that? No. Let there be light. Okay, here we go. Oh. Did that help? It's a bit better. Is there anyone that can't see this? Shh. Is there anyone that would like to say, oh, one more time? Fantastic. That's very nice. Now, if I was good at drawing anime, I'd draw a really big-eyed, cute little kid. And go, oh. Okay, now we've done it. All O's gone. Actually, that's a spaced-out, crazed psycho kid. Look out! He's coming to get you. And he's entirely made of O's. Okay, shh, 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 shh. So here's our machine. Now, you can see there's 16 memory addresses, 4 by 4. I'm just going to write them in a grid because it's easier than one 15-line long. And it's going to help me it's going to help us quickly work out addresses because we can, if I say there, what's the address of this cell? 5. If I say this, what's the address of this cell? 15. 0. Don't forget we start from 0. So if we number the cells 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So each cell has an address. Each cell has contents. The contents of a cell will be a number in the range 0 to 15 because it only holds 4 bits. Let's say initially all the cells are filled with zeros. When you turn the machine on, notice now we have 2 pieces of information about each cell, its address and its contents. Don't get confused. If I rub out the addresses, will you remember they're there? See now, I knew you'd say yes, but okay, this is probably the biggest problem in C, that when we look at a memory cell, we often get confused about whether we're talking about its contents or its address. But yeah, let's just try and make the distinction really clear. So here we are, and we've got 2 registers there, initially zeros. This is a very boring program. Program starts execution in cell 0. Execution continues cell by cell until it reaches the instruction 0 and then it halts. Because if you look at the list of instructions up there, the instruction 0 is halt. The first 8 instructions are called 1-byte instructions and they each take 1 byte. So if I wanted to ring the bell and then halt, what would the program say? 7, 0. This program rings the bell and then halts. Execution starts here, bell rings. Execution continues to this step, 0, it halts. What if I wanted to ring the bell 4 times and then halt? You got it. Are there any loops? You'll have to, well, are there any loops? That's a very good question. Okay, add. Whenever we do any calculations, the computer's sort of wired up so it can only do serious or interesting things on registers.
I have a question.
Yes?
Where's the program counter?
I'm not showing you the program counter. It's in my pocket. You can't have it. What's that?
Don't they all have to have...
Yeah, it's got lots of stuff. I've just abstracted a lot of the stuff away. Yeah, it's got a program counter and it's got everything.
How do we know which instruction it's up to?
Oh, how do you know what it's up to? Yeah, I'm going to use my finger. No, you're right. There's another way I could teach this, but I've chosen to do it this way today only because I thought it would save time, perhaps erroneously. But you're absolutely right. We could store somewhere a program counter that stores the address that we're up to, that we're about to execute. And initially it would be 0, and then when we're about to execute this cell, it would have changed to a 1. But we're not going to. Only because I want to make it really simple, but we'll put it in later on for you. All right, is this cool? This is a program that rings the bell 4 times and stops. It's not a very interesting program. What about if I wanted to, oh yeah, I was just about to say, it's got 2 registers. The computer does interesting things to cells. It doesn't just store values in them. It can do manipulations on them. It can test them, it can print them out, it can add things to them, subtract them, and do all various calculations. Most computers can't do interesting things to general memory. They can only do interesting things to the registers. So a program tends to involve moving stuff into registers, doing operations on them, moving them back. So if I wanted to add the register R0 to register R1 and store the result in register R0 and then ring the bell 3 times, what would my program look like? One 777. Instruction 1 adds register 1 and register 0 and stores a result in here. 0 plus 0 is 0. And then it rings the bell 3 times. Does that all make sense? What are the other instructions we've got? We've got subtract, we've got increment, which means increase register 1, decrement, which means decrease, increment. 4 increments are 1, 3 increments are 0, 5 decrements are 0, subtracts 1 from it, 6 decrements are 1, and 7 swaps the registers around. So if I wanted to compute 4 plus 4, how could I do that so far? How could I compute 4 plus 4?
With the 1-byte instructions?
Using only the 1-byte instructions.
Need to increment R0 up to 4.
I'll need to increment R0 4 times, so that incrementing R0 is instruction 3. So I'll increment it, increment it, increment it, increment it. So when the program's executed these 4 lines, this will have the value 4. What am I going to do now?
Increment the R1.
I could increment R1. Can I do it faster?
7.
Swap. Ring the bell and swap them round. But I wanted to double 4. What can I do now? Add. And then add. Woohoo! Can you do it in less than 7 bytes? That's a challenge for you. Okay. So they're the 1-byte instructions. They all make sense. It's also got 2-byte instructions. Let's have a quick look at those, just very quickly. Instructions 8 and above take 2 bytes. That means after executing one of these instructions, the computer jumps on 2 steps. The second byte we always call data. So if I wanted to print the number 6, my program could start simply with 8. Oh, well, let me write it in the screen. Eight is a print instruction. So if I said 8, 6, and then let's ring the bell just for fun, and then stop, this will print out the number 6. Does that make sense? And I could print out the number 8. Now notice if I print out the number 8, this doesn't print out 8 and then move on 1 and then print out 7. After executing a 2-byte instruction, we jump on 2 steps. So this would print 8 and then execute a 7, which is ding a bell. Does that all make sense? No, wave at me, someone that doesn't. Ask a question.
Can you repeat it?
Yes. It's the problem with 2-byte instructions.
Yes.
Some instructions only take 1 cell to encode the instruction. Like for example, the instruction to add 2 numbers together in the registers, I put here, that only takes up 1 cell. But if I want to tell it to print something out, I have to tell it to print, and then I have to tell it what to print. So that takes 2 bytes to say. So I say, so that instruction is a 2-byte instruction. Which looks like this, 8, 6, say. And that says print the number 6. Does that make sense? And then the next thing it'll execute will be the 7. It won't try and execute the 6. Because it's a 2-byte instruction, so after executing it, it jumps on to the next instruction.
That's why you need the program counter.
I don't need a program counter. Man, you guys are so politically correct. Okay. So, we probably do need a program counter, but I'll never admit it now, will I? Okay. I'm sorry. You forced me into a corner. Okay. Okay, so we got 2-byte instructions, the ones that take a bit more information to represent. 8 prints something out. 9 loads. It copies something from a memory location into R0. So if I said, for example, 9, 1, what does that do? That, no, that was a bad example. I shouldn't have done that. If I say 9, 0, what's that going to do? No, it doesn't set register 0 to 0. It does not copy the data into the register. It copies the cell who the data refers to into the register. So the second argument here is an address. So 90 means copy the contents of cell 0 into the register. So what will that put into the register? A 9. Not a 0. It will put a 9 in. Copy the contents of cell 0. Which is cell 0? Cell address 0. Remember they start address 0, 1, 2, 3? So that's 9, 0. So if I wanted to say the doubling program, double 4, here's a faster way of doing it. I could say 9, 15. Oh. And I don't want to copy it into R0. What about if I copy it into R1? That's instruction 10, okay? What do you think of this program? 10, 15 means load into R1 whatever's stored at 15, which is 4. So that loads a 4 in here. And then I'm just going to add it once and then add it again to make it 8. How many bytes did that take? Well, actually, we said that took 16. Because the way we measure a program is the gap from cell 0 to the last byte that isn't 0. But if you wanted to make the program smaller, what could I do? I could put the 4, where could I put the 4? I could put the 4 in, oh well, yeah, Theo's being clever. I could put the 4 there, and then this is cell 0, 1, 2, 3, oh, what's happening here? 4, 5, 6, no, 0, 1, 2, 3, 4, 5. Addition, I remember that. Oh, counting. So this is cell 5. So copy the contents of cell 5, copy the contents of cell 5 into R0. Cell 5 being a 4, so that would put a 4 in there. Then add, puts it there, and add again, adds the 4 in again, which makes it 8, and then the 0 means halt. But I could even save one more byte. How could I do that? If I was really hacky, I could do this. Look at this program. And this has to be now 4. So let's look at how the program operates now. It goes, load whatever's in address 4 into R0. What's in address 4? The number 4. Into R1, sorry. Load 10 is load into R1. Then add, then increment R1, then halt. It's not 6. That's what we call a 5-byte program. So the number of non-zero bytes up to the... you can define the length of a program however you want, but in this course, for reasons that will become apparent very soon, we're going to say that the length of a program is until you reach the last non-zero byte. Okay. So you get this for free. Although it is executed, you don't have to put it in because it's... Now notice we did a little trick here. This is data when it's loaded in here initially, and then it's an instruction. This is a feature of say the Intel chips, the Pentium and so on, that a program doesn't really know if a byte is an instruction or if it's data. It only knows it from the context in which it's used. So data can be instructions, which is a terrible thing that leads to lots of hacking attacks, and instructions can also be data. They're all just numbers as far as the computer's concerned. Now, did everyone understand that last very cryptic program there? Does that make sense? The only interesting instructions to show are these 3 ones remaining. These are jumps, and these are how we're going to get to a loop. The computer tests R0, and depending on whether it's 0 or not, it will jump to where you tell it. For 14, it'll jump to where you tell it if it is 0, otherwise it'll just keep going. And if it's instruction 15, it'll jump to where you tell it if it's not 0, otherwise it'll keep going. Does that make sense? Your challenge is this. Can you write a program to multiply 2 numbers? So I want the numbers to be put the n down here. Suppose they're going to be 6 and 2. I want you to somehow compute 12. I don't care where you put it when you're finished. Write it back in here if you want, or leave it in a register. We'll be vague about how we return values at the moment. How are you going to multiply 2 numbers when we've only got add and increment? What's that? Jump. You're going to jump, loop, and just do repeated adding. Yeah, does that make sense? So you're going to add either you're going to add 6 2 times or 2 6 times. You're going to load one of them into R1 and then you're going to do 2 or 6 ones. And because it's a variable number, it's going to have to be inside a loop. You don't know in advance until you read this how many you've got to do. So you'll have to do a loop. Does that make sense? And the loop will just, presumably there'll be a counter somewhere that you subtract 1 off each time, and you'll load that counter into R0 and you'll test it to work whether you jump or go straight through. That's your challenge before your tute, is to try and write something to multiply 2 numbers together. Now, just looking at the time, we actually have slightly more time up my sleeve than I thought we would. Let me just jump back past. Wow, what movies were you guys watching? That's awesome. Okay. No, it's here. It's here all along. All right, can you see what's going on? Let me just turn off the lights. Shh, 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 shh. Okay. In tomorrow's lecture, we're going to be talking about abstraction. Remember I said there were the 3 things in science? We did 2 of them today. The last thing's abstraction. We will be, if you want some interesting homework over the week, well, between now and then, play this song from the Darjeeling Limited, an excellent film. And there's an excellent song, Where Do You Go to My Lovely? Very nice song, because that is the theme of tomorrow's lecture. Now, in the small amount of time we have remaining, which is a good 5 minutes, I want to talk about how we're going to apply this skepticism in computing. So when you write a program, you're naturally going to think what? No. You say you're naturally going to think your program fails, but honestly, what are you going to think? It fails. You will probably go through a phase early on in your programming career when you're going to expect all your programs to fail. But after a while, you'll start to write programs that don't appear to fail, and then you'll move to a state of mind, hey guys, shh, 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 shh. It's the noisy corner. Then you'll move to a state of mind where you'll expect your programs to work. So you need to write, what am I going to say? You need to write tests, unit tests, to check your programs to see if they're correct or not. In the same way we were talking about science, you never know if you're right or wrong. We still don't know if the Earth goes around the Sun or the Sun goes around the Earth. Do we know that? I don't know that. I can never work out the difference. As far as I can see, the two are exactly the same. It's like when Einstein said to the conductor, excuse me, when does the platform arrive at this carriage? But maybe there is a difference. I don't understand enough about physics to know. But we never know if the world is flat or round. Really sure. We're never really sure. And until we have a test that fails. So if you write a whole lot of tests for your program, being skeptical, assuming your program's not correct, and yet your program passes all the tests, do you think your program is correct? No. No, you just think, so far, it looks correct, maybe I have to do more tests. How would you, and here's my challenge for you, how would you work out if a binary sort was correct or not? You would test it yourself. But how could you test it? Because the person that sent me this code had written some tests and it tested it. And it passed all the tests. Don't use those tests, make your own. It's always better to use tests that other people have written. The tests you write for your own code tend to be crap. So you will find that from now on, in your assignments, we'll always get you to write tests, and you'll submit the tests, and you'll be marked on your tests, but we'll never apply your test to your code. Whose code are we going to apply your test to? Everyone else's code. And you'll be amazed at how that sharpens your mind when you're writing tests. Because you're now testing other people and you want them to be wrong. Whereas if you write tests for your own, you want them to be right. So I just want to spend the last 3 minutes or so telling you how we do tests. Because you'll be doing tests all the time from now on. Here's our testing approach, just for this course. You've got a file. It contains some function. Maybe it's called binary search. It's going to return an int to say whether the thing's in it. It's got some type signature. There's the function. We're going to call that binary search.c because that's going to contain an implementation of the function. Because that's a function you're going to be sharing with other people, we need to share its prototype. So where do we put the prototype? Where do we put the prototype? binarysearch.h. And up here we'll have the prototype for binary search. Int binary search. This is what your program's going to look like. Now, when you call a program and do stuff, you're going to have a main. And that's just going to be in one thing off on the side. Your main. And your main is going to hash include binarysearch.h. And then it's going to be main. It's going to do some stuff, and then it's going to finish. Woohoo! That's your program. I don't want to see it all mushed together. It's 3 separate files. Or more, if you've got more different classes that we're going to need here. Now, how we're going to get you to test stuff is, at the same time, you're going to write another file called binarysearchtest.c. Does that make sense? Binarysearchtest.c is also going to have a main function. And it's inside it, it's going to have some functions called test binary search and test something else and test something else and test something else. And this main function is going to call all the tests. So you will, when testing, compile these 3 files together and run the tests. And when submitting, you will compile these 3 files together and submit that. Does that make sense? Now, your tests are going to be in binary. The test for this file will be in a file with the same name with the word test put on the end. And if you write another file later on called chess.c, because it's got some chess stuff in it, I expect to see you write a chess. I wish, by the seashore.c. Okay, and so on. So every file is going to have a corresponding test file, and how your tests work is very, very simple. Let me actually write a test file. We're going to say int main stuff. And then we're going to say test, I don't know, what's the first thing we're testing? Test the bounds. Test the bounds. And that's a void function. It doesn't have any arguments. It doesn't return anything. And then we're going to write something called, I don't know, test the splitting. I don't know. I can't think of all the things you'd test for binary search. That's your challenge for this week's lab, actually. And test this. And there's a series of functions you're going to write, each one testing a different thing. The functions don't interact with each other in any way at all. They don't return any values. So if everything works at the end, we're just going to say printf all passed. Woohoo!
But then if they're the narrow, it still prints all passed.
No. Because each of these test functions here, let me show you what a test function looks like. Void, test something void, is going to set up some stuff. Is going to call your function, and then what's it going to do? Assert. Assert the answer that you just got equals 42, double equals 42. And up here you've said answer equals binary search of, okay. So the idea is your test files contain a whole lot of asserts. And if the test passes, the asserts don't fail, and everything proceeds silently. And if the test fails, you find out where it failed. Does that make sense? We have a slightly more elaborate structure than that, and we'll tell you more about it in your tutes. Okay.
Cubicle, he sits down, preparing to work. Code monkey not thinking, so straight. Code monkey not feeling, so great. Code monkey like Fritos. Code monkey like Tab and Mountain Dew. Code monkey very simple man. Big warm fuzzy secret heart. Code monkey like you.
Go. See you guys.
Code monkey like you. A lot. Code monkey have every reason to get out this place. Code monkey just keep on working. See your soft pretty face. Much rather wake up, eat a coffee cake, take bath, take nap. This job fulfilling in creative way, such a load of crap. Code monkey thinks someday he have everything, even pretty girl like you. Code monkey just waiting for now. Code monkey says someday, somehow. Code monkey like Fritos. Code monkey like Tab and Mountain Dew. Code monkey, very simple man. Big, warm, fuzzy, secret heart. Code monkey like you. monkey like you.